Okay, so we're going to look at the Macaulay method for beams, but to start, we're going to start with, I guess, getting an understanding of what the Macaulay method is. So when you have Macaulay brackets, kind of like that, this basically expresses a, what do you call it? A piecewise function, right? So when x is anything less than a, then the function is turned off. So basically, the function is 0 when x is less than a, and then the function is whatever is in here when x is greater than or equal to a. So it's that when x is greater than or equal to a, right? So in the lectures, we kind of like expressed it differently. In the lectures, it was written as 0 when x is less than or equal to a, and then it was the function itself when x was strictly greater than a. And if you choose to do either one, it doesn't matter. It's going to give you the same answer, because if you substitute x equal to a over here, you're going to get 0 anyways. So it doesn't really matter too much. The one thing you do need to understand is that this basically has the function turned off when x is less than a, and the function turns on when x is greater than a. So an example would be, let's say you wanted to express a constant, right? So let's say you wanted something like this, where the function switches off up until it reaches some point, and we'll call this a, and then it must equal b, and it must stay constant until. Cool. So the way you would express this using Macaulay brackets is you'd have b, right? And over here, you're going to specify where you want it to switch on. So we're going to say x minus a, and a is the point where we want it to switch on. Then the power is going to indicate how the function looks, right? So just to kind of repeat, so this point over here, this a over here, is basically where you want your function to switch on, and then the power is going to indicate how the function looks. If it's to the power 0, then you can kind of imagine it, this function over here is going to switch on only when x is greater than a, right? So if we were to express it, I think expressing it as a piecewise function will make sense. So you're going to have b times 0 when x is less than or equal to a, and then you're going to have b times x minus a to the power 0 when x is greater than a, right? Cool. So when it's less than 0, obviously this will simplify to 0. So we've covered this portion, right? Then this portion over here is going to equal b. Or you could just say b times 1, which is still b. So if you wanted to express something that's constant, you would raise the Macaulay brackets to the power 0. Now, it doesn't mean that this is automatically b for every single value of x. Remember, the Macaulay brackets kind of splits the function up. So it will be 0 when x is less than a. Then when x is greater than a, then it will become b multiplied by this whole bracket thingy, which is just going to be 1. Cool. I hope that kind of makes sense. So if you wanted to do like another function, let's say you wanted b times x, right? So you wanted to express a graph that looks like this. So it starts it's switched off, and then it continues up with some gradient b, right? Then this would be expressed as b and then x minus a. So your starting point is a is where the function switches on, and then this is going to be to the power 1, right? Reason why it's to the power 1 is because you have b, which is your gradient, and that changes as x changes. So in essence, if you simplify this, you're going to get b times 0, because this bracket is 0 when x is less than or equal to a. And then you're going to get b multiplied by x minus a to the power 1 for x greater than a. So essentially you're going to get an equation for a straight line, right, when x is greater than or equal to a, right? So yeah, I hope that kind of makes sense. Then applied to beams. Essentially what we're doing when we use the Macaulay method for beams is we're trying to write an equation for how the internal loads look inside a beam. So if you think back to SWK, where you had, let's say you had a scenario like this, right? And then you wanted to find like the shear force. You wanted to like write the shear force diagram and the bending moment diagram and stuff. So the long method that we were taught was to section the beam at different points, calculate the shear force, and then draw the shear force diagram and bending moment diagram. With Macaulay, that's essentially what we're doing, but we're writing it as one big equation. So if you remember back to SWK, you'd have to do an equation for this part. So for this part of the beam, and then wherever you had a change, you had to section it there. So we have this force over here. So we'd section just to the right of that force, calculate again. Then we have nothing up until this point over here. You're going to have some reaction. Then you calculate again, right? So that will give you a total of 3 different equations, right? With the Macaulay method, we write all those 3 different equations in one, and we account for those discontinuities. So essentially what we're going to do with the Macaulay method is we're going to write one function for this portion over here, and then another function for this portion over here, right? And we're going to express the jump caused by this force as like a discontinuity. I hope that kind of makes sense, but yeah, if it doesn't, it's fine. Hopefully it makes sense after we do this example. So with this example over here, the first thing we do is write down or draw the free body diagram, right? So we have a reaction here. I'm going to call that RB. We're going to have a reaction here. We're going to call that RA. And then we have our load P. And then this is just L over 2. Then this is L over 2. Cool. Now, if we wanted to express the shear force in the beam, right, we can see that from this point up until just before P, we're going to have the shear force equal to RA. Okay, if you're unsure, I do not recommend you do this in the test. It's going to take forever, but you can section the beam just before the load P, and then this is going to be your shear force. Then you can do sum of forces in the Y equal to 0, so then your shear force is equal to RA, right? Cool. That's a long way of doing it, but we could kind of do it via inspection almost. So our shear force Okay, let's do it like this. So let's ignore every single force that's on the beam right now, and let's only focus on RA. So this is my entire beam with the length L, and I've just got RA. Okay, so now we sit and we analyze, how is RA going to affect my shear force? So we're going to get a constant shear force from RA along the entire length of the beam. Doesn't matter where I section it. I can section it here. If I section it there, and let's say I call this length L over 3. If I draw that length L over 3, so I have RA here, and then I have my internal shear force. Then if I do sum of forces, my internal shear force is equal to RA. I can section it here. Let's call that length, 4? No, 3 over 4 times L, or whatever. Then if I draw that entire length, I'm still going to get my shear force equal to RA, right? So RA is a constant force that acts along the beam, right? Cool. So I know how to write the Macaulay expression for a constant thingy, right? So it's just going to be B, which is going to be my RA, because that's the thing that's constant. So the shear force is going to be equal to RA, right? And it's going to act along the entire length of the beam, right? Cool. So the first part of my shear force expression, V of X, is going to be RA, right? Then in Macaulay brackets, X minus, and then now I need to identify where this force starts. So it starts at X equal to 0 over here. So it's going to be RA X minus 0 to the power 0. Cool. That's the first part. Then I have another load, P, over here. And then that's negative because it's acting down. P, X minus. Now I look at where the force starts. So it starts at a distance L over 2. So from here, it's 0, 0, 0. Then all of a sudden I encounter P at a distance L over 2. So I'm going to write there L over 2. And then to the power 0 because it's constant. If it was a distributed load, then you'd have something different. Okay, and then plus again, I have this load RB, and I can account for it by saying RB X minus, and RB acts at a distance L, right? So I can write that. Now, if you look specifically at RB, it acts at a distance L, right? And it switches on from there. But to the right of it, there's no beam, right? So, okay, how do I explain this? Okay, so our beam starts from X equal to 0, and it ends at X equal to L. So this over here is the domain of whatever equation we're deriving. So we're deriving an equation for our shear force, so that's going to be the domain of our equation. Anything past L doesn't exist. There's no beam there to have an internal shear force. You can't have an internal shear force at L equal to 1 over here. There's no beam there, right? So that's our domain of our function. So the only point where RB can act is at point L. Anything past that point, it's not acting, right? And it doesn't act before point L. RB is not present here. So any sectioning that you do before here, before this point over here, won't include RB. Hope that makes sense. So if you were to plug in the only value x can be for RB, which is L, you'll get 0, right? So this thing over here is equal to 0, right? Which makes sense. We expect our shear force at x equal to L to be 0. So that means that this thing minus that thing must be 0 when x is equal to L. Okay, I hope that kind of makes sense. So this RB thingy is 0. So then our final shear force equation we can just write as R of A x minus 0 to the power 0 minus P x minus L over 2 to the power 0. Or we could simplify it further. This RA over here acts along the entire length of the beam, right? So it starts at 0, and one thing about the Macaulay brackets, it doesn't tell you where the force ends, right? So it's just on until mathematically. So if you go back to this example, this thing is off at this point, then it switches on, but the Macaulay brackets can't say when to switch it off, right? It's just going to continue on forever for however long x is defined, right? So if x is defined up until infinity, this will carry on until infinity. But our beam over here is defined up until L, so RA will continue up until L, if that makes sense. Hopefully it does. So we can simplify this then to just RA, right? And then this part we can't simplify. If we were to just simplify this to P, then we're implying that P acts along the entire length of the beam, but P starts at L over 2. So we still need these Macaulay brackets. So we're going to put them in P x minus L over 2 to the power 0. Cool. Hope that makes sense. And then, yeah, you can also get the bending moments as well by differentiating this. And then, integrating that, and then solving for the constants using your boundary conditions. So the boundary condition here, there mustn't be a moment here, there mustn't be a moment there. So you can plug that in and solve for your boundary conditions. But if I'm not mistaken, there are thingies in the formula sheet on how to solve the bending moment equations. There's like the Macaulay brackets for different bending moment cases in the formula sheets, if I'm not mistaken, right? But I guess I could try and solve for it. So if you were to consider the bending moment for this example, I'm just going to move this one down. If you consider the bending moment for this example, you have RA, right? RA is going to induce a moment along the entire length of the beam. So no matter where you section, RA is going to have an effect on the moments in the beam. So if you section here, right, you're going to have RA, and then I'm going to call this length X, and then what's the convention? I think it's like that, right? So this is your internal moment, right? We've sectioned the beam at some distance X, and now we're looking at the moment caused by RA, right? Cool. So RA is going to cause a negative moment according to our convention, but then this is counteracting it, so it's positive. Never mind that. Hopefully you can see that depending on what X is, the moment caused by RA is going to change, right? So we expect the moment to be some function of X, right? Cool. We don't expect it to be constant, because as X changes, So if x becomes much larger, then you're creating a larger moment caused by RA. So then your moment itself will be larger. Cool. So the way you would write it in your Macaulay brackets is RA. So the force itself remains constant, if you remember from your shear force, right? So the force itself remains constant over here. But now we're multiplying it by some distance, okay? So it's going to be x, and we're going to say, because it starts at 0, the moment it causes also starts from 0. So we're going to have a moment here, until, right? Caused by RA. So we're going to say minus 0, and then now it's to the power 1. Okay. And then if we look at this diagram over here, our moment M must be equal to RA times X, right? And we expect to get the same equation over here. Okay, so if we simplify this, what do we get? We can simplify the Macaulay brackets themselves and say that x minus 0 to the power 1 is equal to 0 when x is less than or equal to 0, and then we get x minus 0 to the power 1 when x is greater than 0. Okay, so we basically get, from this, we get x when x is greater than or equal to 0, or greater than 0, however you want to write it. So this thing over here checks out. This over here, that checks out. So if we simplify our Macaulay brackets, we're going to get RA times x. Okay, that's obviously not the full thing for the moment, that's just RA. Then we move over to P. So P acts at a distance L over 2. So we're going to get a very similar thing. We're going to get minus P, and then we're going to get x minus L over 2 to the power 1. Okay, so the moment caused by point P will only start having an effect on the beam after P is applied, if that makes sense. So for this portion of the beam, there's no P, so there can't be a moment induced by P. It's only after that point. So over here, that's the only point where there can be a moment caused by P, right? So cool. That's what we're going to get from the force P. And then RB, if you think back to what I explained for the shear force and how RB is 0 at a length L, or rather the Macaulay thingy is 0 at L. I guess to explain it for the moment, you won't have any distance to multiply with once you get to this point. So you could write it as RB x minus L to the power 1, right? But then when x is equal to L, then yeah, game is cooked, bruh. So you get 0 here. So this automatically falls away, that's 0. So then this is equal to RA x minus 0, or put simply RA times x, right? And then minus P x minus L over 2 to the power 1. Remember, you can't simplify this, you can't simplify that to just P times x, because P only starts at a distance L over 2. So you need the Macaulay brackets to say, okay, P is only going to have an effect after L over 2, right? Whereas this one we could simplify because RA starts at 0, right? So it starts at the beginning of the beam. RA is going to have an effect from 0 all the way to L, and that's where the beam is defined. Cool. I hope that makes sense. And then if you wanted to write the distributed load equation, we know that there's no distributed load on this beam over here, right? So how do we express something that's 0 using Macaulay brackets? We can go outside the domain. So just like we did with, or just like we found, this was 0, right? So this thing over here, just like we found that was 0 when x is equal to L. We could do the same thing. So Q is equal to whatever function Q of x would be, because it's not there, could be literally anything. Then that's only, or let me just say Q minus L, and then yeah, depending on what Q is, could be to the power 1, could be to the power 0, but yeah, that's how you'd write it. I don't think this is necessary, but anyways, then cool. The next question, this one over here, if you wanted to write an equation for Q along the length of the beam, so Q is a uniform distributed load in this case, so we expect Q to be constant throughout the length of the beam, right? And Q starts from 0 up until a length L, right? Cool. So our Q of x will then be Q, and then multiplied by x minus 0 to the power 0. So remember, to the power 0 implies that it's a constant. If it was to the power 1, then we'd have Q changing with x, right? But because this is 0, you'll just get Q out of this, which is cool. It's constant. And then our shear force, right? If you think about the shear force, okay, first things first, free body diagram. I forgot about that. Don't forget about that tomorrow. So you have RA, you have RB, and then you have the distributed load, right? Cool. So our shear force, we expect RA to have an effect through the entire length of the beam. So our first term we could write as RA, and then RA has a constant effect, doesn't change as x changes, right? So x minus 0 because it starts from 0, and then to the power 0 because it's constant. Then our distributed load, however, has an effect that changes with x. So if you were to section a portion of the beam, we'll call this x, call that RA, and then you have your distributed load that acts along this portion. Then you have your shear force, right? So your shear force is going to be some combination of RA plus some combination of your distributed load. So plus Q times x, right? Cool. So if we wanted to express this Q times x with Macaulay brackets, you can see that this Q times x is an equation of a straight line where Q is your gradient and x is x. That's your variable, right? Cool. So if you go back to that example that we did, we wanted to stay, or, well, we don't want it to stay off, but like, remember this example where it was off and then all of a sudden it was on? Okay, so we want something like this, but we want it to be switched on from the get-go. Okay, so to write this portion over here, to write that portion, we're going to say plus, and then q, which is going to be our gradient, and then our equation. So our equation is going to be x minus 0 to the power 1. Okay, so remember, to the power 1 gives you an equation of a straight line. So if we express the Macaulay what as a piecewise function, we're going to get this. Right, and then this. This simplifies to just x, right? Which, if you substitute back here, you're going to get qx, right? Which makes sense. It checks out with what we derived over here. Okay, so in essence, our Macaulay function for our shear force is going to be, let me just erase all of this. Our Macaulay function, or whatever, is going to be RA, right, minus 0 to the power 0 plus q x minus 0 to the power 1. Cool. We can simplify this. This will just become RA, and then we add q of x. Well, q times x. Cool. That's our equation for our shear force. And then to get the bending moment, you can again go to the formula sheet. There are examples on how to get the bending moment using, or when you have a uniform distributed load, there's a Macaulay equation for the bending moment. But essentially we're going to get m of x will be equal to RA x minus 0 to the power 1 now. So you could think about it, if you were to integrate this, the power here will be 0 plus 1, and then 0 plus 1, then RA, it's going to be RA divided by 0 plus 1, which is just RA, so that remains constant. And then the power of here is increased by 1, and then the q term over here, so you're going to get plus q over 2 now, because plus 1 over 1 plus 1, so it's going to become q over 2 x minus 0, and then that's squared. Cool. I hope that makes sense. Hopefully it does. And okay, the sign for this is incorrect. Okay, so the q is negative because it's pointing down. So our distributed load is pointing down, so that's supposed to be negative. RA is positive because it's pointing up. Okay, so for the shear force, if something's pointing up, we regard it as positive. Something is pointing down, it's negative. And then obviously if you were to integrate this equation over here, your signs won't change. So you'll get this, where this term over here is negative and that one stays positive. Cool, hope that makes sense. And then in the case where you have a non-uniform distributed load, I guess, you can simplify the distributed load into two sections, right? So just like you did in SWK, where you'd consider the triangle portion and a rectangular portion. So I'm just gonna write this bottom portion, and then you're gonna have your triangular portion. Okay, so you're gonna get Q, then Q over 2, and then reaction forces. Cool. So if you have this case and you're trying to find Q is going to be the sum of this portion and the bottom portion, right? So for the bottom portion, we have a constant. So the bottom portion just looks like this, right? And it's acting at Q over 2. Cool. So for the bottom portion, we're going to get Q over 2 x minus 0 to the power 0, because it's constant, it doesn't change with the length of the beam. Then we're going to add to that the triangular portion now. So the triangular portion, if you think about it, this is just a straight line, right? So if I were to graph it out, this is just a straight line, kind of like that. So it starts from Q over 2, and then it ends at Q, and it continues for a length L, right? Now if you wanted to get the equation of this line, you'd do y is equal to mx plus c, right? Cool, then you solve, right? But okay, okay. Okay, this y is equal to mx plus c thingy, this graph over here, describes the entire distributed load. So if you kind of think about it, you have your rectangular portion, let me draw it in pink. You have your rectangular portion here at the bottom, and you have your triangular portion at the top, right? Cool. So forget what I said about adding the two together. Why is that? We'll just work with this entire equation, right? So the top part, or rather the equation, right? We can get the equation using y is equal to mx plus c. We know that c is going to be equal to Q over 2, which is that pink portion over here. And that's the portion that remains constant, right? So that's our Q over 2. And then the other portion of the equation is this m times x. We can get m by simply doing delta y over delta x, which is going to be equal to q minus q over 2 divided by L minus 0. So q minus q over 2, that distance there, divided by this distance here, right? That's going to give us q over 2L. Okay, so we expect the equation for our distributed load to be Q over 2L times X plus Q over 2, right? That's our entire equation for our distributed load. So it's basically the equation of this line over here, and it's been shifted up by Q over 2. So it's been shifted up by that much. Yeah, I hope that kind of makes sense. So if you were to write it in Macaulay brackets, right, you'd write this portion over here has an x in it, right? And it starts at x equal to 0, right? So you'd have Q over 2L x minus 0 to the power 1, right? Equation of a straight line. Then for our constant part, we could also express it in Macaulay brackets by saying plus Q over 2 x minus 0, because the constant part starts at 0, and then all of that to the power 0, because this part is constant. Now, if you had a case where, let me see if I can think of another case. Let's say you had something like this, right, where it starts at a different point. Let's call it A. So let's say it starts at A, right? Your Macaulay brackets are going to look a bit different. So let's say that's still Q over 2, and then let's assume that's still L. So let's assume that the function itself doesn't change. It was just shifted now, right? So it's going to be off for this portion, and then all of a sudden at this portion it starts acting. So your graph would look something like this, where your distributed load is switched off. Then as soon as you get to point A, your distributed load has a value of Q over 2, right? So this value over here is Q over 2, and then it continues as a straight line up until you get to Q, right? So to express this in Macaulay brackets, you would get Q of X is equal to, and then you'd write the gradient. So I'm doing the QX part, so this part over here, and assuming that everything remains the same, like L is the same and all of that, so the equation itself doesn't change. We're just changing the starting point. So we're going to get Q over 2L, I believe it was. Then the starting point is now at A, so x minus A, and to the power 1 plus Q over 2 x minus A to the power 0, right? And we can't simplify this to just Q over 2. So this is not equal to just Q over 2 because it starts at A. If you just say it's Q over 2, that means this is defined as Q over 2 everywhere. But over here, it's 0. Then once you get to A, it's defined as Q over 2. Hope that kind of makes sense. And then another way, if you're still confused, hopefully this kind of clears it up for you. So this portion over here if I write this portion over here, so let's just rewrite it just to minimize the a part. So I'm just going to rewrite this as q over 2l x minus 0 this time. So back to this example, right? So if I write it as that, this simplifies to q over 2l times x, right? Which is the equation of a straight line like that, right? But you can see that this is missing the bottom part of our distributed load, right? So there's no rectangular portion. We're only dealing with the top part over here. Okay. Then the bottom part, the rectangular part, is described by this part of our function, which is q over 2. And then if I say x minus 0, so again, we're describing this example. So x minus 0 to the power 0, we can simplify that to q over 2. If we were to graph this, this describes this thingy over here, right? Cool. So this is q over 2. And this starts from 0, right? And it ends at, this will end at q over 2. Okay. But our entire distributed load is this thing plus that one, which gives this one. So it's that plus this, right? Yeah. Okay, that's a bit explanation. I hope that makes sense now. Okay, and I hope this whole example makes sense. Then another thing with Macaulay brackets, where's that example? Okay, it's fine. Another thing with Macaulay brackets is that it doesn't tell you where things end. It only tells you where it's starting, right? So we could have a situation like this where we have a distributed load, but it's only in the middle. So let's say we have that, and we have these reaction forces, or RA, RB, but we have now a distributed load in the middle that acts along a length L, right? Cool. Now we want to write the Macaulay expression for this. So we want to write a Macaulay expression for Q. So Q of X is going to be equal to Q, and then because it's a constant, so sorry, not X minus 0, X minus L, and then to the power 0 because it's a constant. So X minus L indicates that it switches on at L, so starts at L, but this implies that it continues on until the end of the beam. So it doesn't indicate where this thing is going to stop. So what we have to do is we also have to subtract everything after it. So this thing tells us this, right? Where we have our original L, but it continues acting up until the end of the beam, right? So we don't want this portion over here. We only want that portion. We want to scrap that. So the way we deal with this is by subtracting it. So we'll subtract Q X minus L, X minus 2L to the power 0. So when X reaches 2L, so this point over here, we don't want a distributed load anymore. So that's the point where we're going to start minusing. So that's why we add that negative there. Cool. I hope this makes sense.